All right, today we're going to talk about polynomial functions. We already know a little bit about polynomial functions because a quadratic equation is a type of polynomial function. A linear equation is a type of polynomial function. So polynomial functions, when you write the general form, I find that all the variables and the constants, it makes it a little bit confusing, but it looks like this. So it's going to start with f of x equals, or p of x equals. And it's going to have a coefficient and then x to some number. So it could be like x to the 5th, x to the 4th, whatever. It could be x to the 20th. And then plus, and then a new coefficient, n minus 1. And then, yeah, x to the n minus 1. So here's the important thing. The exponent goes down 1 each time when you're writing it in standard form. So if this was 5, then 5 minus 1 would be 4. So that would be x to the 4. And the next one would be n minus 2 because you're going down 1 each time. You don't need to learn this general form, but you should be able to understand what it's saying. So the a's are all constants, so they could be any number. It could be like 5, 10, 15, 20. They don't have to be multiples of 5. The x's are just x, the variable, and the exponents go down 1 each time. And that goes down all the way until you get to a sub 0, which is the last term, and that one doesn't get an x. So you can kind of see that here. You can see the exponents go down 3, 2, 1, and then the last one does not get an x on it. It's a constant term. All right, so coefficients are the numbers that go in front of the x's. They are multiplied by the x's. So we're going to circle the coefficients here. What will be the coefficient of the first term? I see a negative sign there, but I don't see a number. What number should I put? Right, so altogether it would be negative 1, right? So that's a coefficient. What's the next coefficient? Just 4, yeah. So coefficients, when you take the x's off, just the numbers that are multiplied by them. And then the next one? Say it again? Negative 1/5. You guys hear how he included the negative? You need that. All right, the exponents must be whole numbers or else it's just not a polynomial. So checking our exponents, they're all whole numbers. And we have exponents of 3, of 2, and this one, if it doesn't have an exponent, it would be to what power? 1, good. All right, every polynomial has a degree. A quadratic is degree 2 because in the quadratic, the biggest exponent is 2. So for the degree, you just look for the highest exponent and you circle it. So what number is the highest exponent? 3, yeah. Leading coefficient is the coefficient of the term with the highest exponent. So the term with the highest exponent is this one, negative x to the 3rd. And from that term, what is the coefficient? We said it already. What was it? Negative 1. So the coefficient, so the degree you find, the leading coefficient, you find the one with the biggest exponent, but you don't take the exponent, you take the number in front, the coefficient. So that's called the leading coefficient. We also can talk about the leading term. The leading term would be the whole negative x to the 3. And then the constant term is the one that doesn't have an x. So that would be what number? 17, good. And it is the y value of the y-intercept. And the reason is because when you find your y-intercept, you put 0 for x. So if I put 0 here and here and here, I'm just going to be left with a 17. So it is the y value of the y-intercept. We have some polynomial functions. We have y equals a constant. That could be any number. It could be like 1, 2, 3. It could be negative 15. I'm going to put C just to represent any number. It could be a number. We have a linear function, and the most simple one is y equals x. And for a quadratic, the most simple is y equals x squared. For a cubic, the simplest one is y equals x to the third, but that doesn't really show the shape of the cubic very well. And so I'm going to give you one that's not the most simple. We're going to do this one as just an example. Y equals x to the 3 minus x, that's a cubic, because the degree is 3. And then a quartic, the degree is 4. I'm going to give you one that shows the shape pretty well. Y equals x to the 4 plus 2x to the 3 minus x squared minus 2x. And notice that one doesn't have a constant term, and neither does this one. And then finally quintic, and that would be degree 5. Can you have a polynomial that's a bigger degree than 5? You can. I just don't have a special name for it. And that doesn't mean nobody has a special name for it. It just means that once you get to higher degrees, people don't use those names as often. So I'm going to write this one down. And then what we're going to do is we are going to draw sketches. I'm going to have you guys open up Desmos. And we're going to sketch these. We are not going to be that exact. We're just going to try to get the shape of them. The first one would be y equals a constant. We can pick any number. So like, for example, if I wanted to graph y equals 2, it might just look like this. It's going to go straight across like that. Notice I didn't make any markings to indicate that was 2 because this is just a simple sketch. So in your Desmos, sketch the rest of these real quick. All right, take a minute and compare your graphs with Layla's. Like I said, we're not trying to be super exact. We didn't put numbers on it, but it should have the general shape that matches the general shape of Layla's.
Yeah. So it was like her favorite song during and something. And then
It's like different from what he actually got me saying no.
And then everybody was just like, oh, like add stuff that is like more specific, like it, so you can actually get stuff. It's so like getting those things everybody else did. I just forgot.
Grab your notes and try it a few more times and start to work. Which ones are not polynomials? So I have a vote for 1. Anybody else want to vote for 1 not a polynomial? You agree? Okay. Why is 1 not a polynomial? Nick. Negative exponent. Who agrees? Right. All right. So you cannot have a negative exponent. And the nice thing is, if we say no, we're done. So you cannot have a polynomial with a negative exponent. So 1 was a no. And what was the other one that was a no? There's another one. So your coefficients have to be real numbers, and your exponents have to be whole numbers. So Scarlett is wondering if it's 4. Anybody want to say it's 4? They're not sure. Why are you saying 4, Scarlett? Which x? Mm-hmm. So here we have an x in the exponent instead of a number, right? An x could be any number. So it could be a whole number, but it could also be like a 0.5 or a negative number. So I agree with Scarlett that this one would not be a polynomial because of the x in the exponent. When the x is in your exponent, that's actually called an exponential function instead of a polynomial function. So this one is no. And the exponent cannot be x. All right, so now we have the work to do for the yeses. Let's do 2 together, and then I'll have you guys do 3. I'm going to switch to something, maybe a pen, because I need to write a lot in here. All right, so first we're going to put it in standard form. When you put it in standard form, you're putting it from the biggest exponent to the smallest exponent. And so for part A, writing in standard form, it would be y equals negative x to the 4. And then the next exponent would be 3, so it would be plus 1/2 x to the 3. I don't have any x to the 2's, so the next one is just x, so it would be plus 4x. And then finally my constant term minus 5. So standard form is when you do the terms in order of their exponents from biggest exponent to smallest exponent. For B, it says state the degree and the type. What's the degree? Look at the top about what degree means. What is the degree of this polynomial, Layla? 4. Who agrees with 4? One person does, 2 people do, 3 people do. Nice. Okay, it's right. So the degree is 4 because it's your biggest exponent. And if it's 4, then what's its name? It's not quadratic, it's degrees 0, degree 1, degree 2, degree 3, degree 4 is called quartic. Quartic. Like a quart of milk, quartic. C, state the constant term. Constant term is the one that doesn't have x. So what would it be? -5, very good. And D, state the leading term. Now this doesn't say just the leading coefficient, it's the whole leading term. So you look for that biggest degree, and then what would the leading term be? So the leading coefficient we know is -1. The leading term is negative x to the 4. So that's just the whole term. You will be asked both things in your delta math, both leading coefficient and leading term. So if it's leading coefficient, just the number in front, and leading term, it's the whole term. All right, go ahead and try 3 now. All right, folks, compare your work number 3. Oh, you just need to know the names from the top, from the paper here. So if the degree is 5, it's quintic. If the degree is 4, it's quartic. Hello. All right, folks, you are supposed to be comparing your work to number 3. Okay. The fundamental theorem of algebra in MathSpeak says if p of x is a polynomial of degree greater than 1, then p of x equals 0 has exactly n roots, including multiple, which are repeated roots, and non-real imaginary roots. And what this means is if your equation has degree 1, just like a linear equation, y equals 2x plus 5, there's one answer. If it has degree 2, like a quadratic, y equals x squared plus 5x plus 2, It has two answers. You guys remember when we talked about quadratics having two answers? And if it is a degree 3, like y equals x to the third plus 5x plus 7, it has 3 answers. Now, some of the answers are imaginary, so if they are imaginary, you will not see them cross the x-axis, and some of them are repeated. So for example, if you had the quadratic equation, and I'm just going to put this in the margin, if you had the quadratic equation y equals x plus 2 times x plus 2, and you set that equal to 0 to find your solutions, and you would get x equals negative 2 twice, that's called a double root. That means that negative 2 is an answer 2 times. So it does have 2 solutions, it's just that they're the same number, okay? So quadratics always have 2 solutions. Cubics always have 3 solutions. That's the fundamental theorem of algebra. So it says we can identify real roots as x-intercepts, and non-real, which are imaginary roots, always come in pairs, and we never see them on the graph because they're not going to cross the x-axis. And when I say we never see them, we can see hints of them sometimes, but we're not going to actually see them. So non-real, which are imaginary roots, they come in pairs, and we don't see them on the graph. So they're not going to cross the x-axis. However, you can kind of get a hint that you're going to have them sometimes, because if my function had zeros, it would dip down like this and show you the zeros, right? If it has non-real zeros, it dips down sometimes like it's trying to make zeros, but it doesn't quite make it. When I see something like this over here, that's telling me there might be some non-real zeros, but I don't have to guess at it. There are other ways to know, okay? All right, so in here, we're just going to simplify the fundamental theorem of algebra. All right, and we're simplifying the fundamental theorem of algebra to say the degree is equal to the number of roots. It's as simple as that. Degree is equal to the number of roots. All right, another way you can know about the degree is by the turning points. So notice that my function here, it has 1, 2, 3, 4 x-intercepts. So, sorry, you can't see that. It's over here. 1, 2, 3, 4 x-intercepts. So it might be degree 4. But it also has 1, 2, 3 turning points. So the number of turning points is 1 less than the degree. But it's not exactly that. I'll tell you that in a second. So it has up to n minus 1 turning points. So if I have 3 turning points, I know that the degree is at least 4, but it actually could also be higher. So if I have, I'm going to write that note here. If I have 3 turning points, the degree is at least 4. Now, when we ask you a test question on this, we're not going to try to be tricky about it. If there are 3 turning points on a test question and we ask you the degree will be 4. But I want you to know that that's not always the case. The degree could be 5 or 6 or 7 with 3 turning points. And so here this is saying if it has a degree of 3, that means it would have 3 total roots and at most 2 turning points. So we're going to do one of these problems together, and then I'm going to give you some time to work on one. Let's look at the first one. We already counted the turning points. The turning points are when the graph goes between increasing and decreasing. So you've got 1 here, 1 here, and 1 here. So we have 3 turning points. If you have 3 turning points, is the degree more or less? It's more, right? So the degree is more. So then the degree would be at least 4. And for our purposes in this class, you can just write 4. That would be fine. So if it is degree 4, the type, that comes from the front where we had all those names. We had linear, quadratic, cubic, quartic, quintic. So degree 4, what's the name? Quartic. All right, any polynomial without restrictions on it is going to have the same domain because it's going to start on the left and it's going to continue to the right. So the domain would be negative infinity to what? To positive infinity. I know that this function looks really tall, like it's only going up, but it's not only going up, it's still going left and right. So this one, it is still going left, still going right, and so the domain is negative infinity to infinity. Sometimes the range will be negative infinity to infinity, and sometimes it won't be, so you just have to look carefully. Does this function have arrows going down? No, so it has the smallest number, and it looks to be about negative what? Negative 6. You want to include the negative 6 with a square bracket. And then it continues going all the way up to infinity. Nice. I'm going to go back up here before we do the bottom part. All right, so a reminder about increasing and decreasing. To do increasing and decreasing, we only look at the x numbers. And so I'm going to ask you to put a negative infinity on the left and a positive infinity on the right. Negative infinity on the left and positive infinity on the right. And then I draw a little line connecting the turning points to the x-axis just to help me focus on the x-axis. And it's a little bit tricky to identify exactly what these numbers are because they're a little bit off. I'm looking at negative, I'm going to just call these 0.5. So I think I have a negative 3.5 and a negative 1.5. And if you want to be a little bit more exact than me, that's okay. So I have negative 3.5 here, negative 1.5 here. Oh, and what's this one, 2? Looks to be 2. So for our intervals, we're going to be using these x numbers. Negative infinity, negative 3.5, negative 1.5, 2, and then positive infinity. These are the numbers that we're going to use in our intervals. As we read it from the left to the right, does it start increasing or decreasing? Decreasing. So we're going to put our first interval under decreasing, and it's negative infinity, negative 3.5. And it switches between decreasing and increasing. So it's going to be increasing next, and this is going to be this interval right here, negative 3.5. Negative 1.5. Then it's decreasing. And then it's increasing again. Questions about increasing and decreasing? I went through that really fast. Take a minute to process and think about what questions you might have. End behavior. It's been a while since we've done end behavior, but we did this with quadratic functions. So we talk about as x goes to negative infinity. Oops, I forgot my s. As x goes to negative infinity. So as x goes to negative infinity, y goes to what? Infinity. And then we talk about as x goes to positive infinity. Okay, so as x is going to positive infinity, the y is going to? It's positive again, good. Because both sides are going up. All right, total number of roots is equal to the degree. So how many roots are there? There are 4, good. The real roots are x-intercepts, and it's a little tricky because it looks like maybe it bounces off the x-axis here, which is something we haven't quite talked about yet, but it doesn't. It crosses it twice. So I'm seeing 1, 2, 3, 4 real roots. All right. there are 4 roots altogether, and there are 4 real roots. So that means there are how many imaginary roots? 0, right? They can only be real or imaginary. So if they're all real, then none of them are imaginary. Then it says to state the zeros from the graph. So you're just writing down where does that graph cross the x-axis. And you don't have to write them as points, only if it says x-intercepts. So I'm seeing -4, -2, -1, and 3. Are you guys seeing the same numbers? -4, -2, -1, and 3. Yes. Not technically, but it's good practice because you're just listing them. Okay. All right, folks, please check your work and let me know what questions I can answer. Yes. For which number? Or do you have slightly different numbers because of where they turned? Yeah. So, folks, there's been a question, like, if I have a slightly different number because I estimated differently on these graphs, is that okay? And yeah, it is. Like, these graphs are hard to read. I'm not too concerned about that as long as you're doing it about right. Any other questions? Okay, I'm going to leave that up for a minute, and then we're going to go to our groups.